เคเริ่มทำการบ้านอันที่แล้วก่อนเลยแล้วกันนะยังไม่เสร็จเลยแล้วค่อยเดี๋ยววีค5ต่ออันนี้ก็ยังใกล้จะเสร็จละแค่ลองดูนิดหน่อย test i j I เดี๋ยว I จุด decision factor dot value dot var เป็น9ขึ้นกับ11เนาะ dot card เป็น22แล้วก็ dot value ให้เป็น1001เสร็จแล้วก็ j เท่ากับ I k เท่ากับ I เสร็จแล้วก็ I dot random 10เป็นตัวนี้ถูกแล้วถูกไหม j dot random 10เป็นตัวนี้ซึ่งไม่ถูกไหมแล้วก็ต้องเปลี่ยน dot value เป็น0.999 0.001 0.25 0.75ส่วน k value ก็เป็น 0.999 0.001 0.001 0.999 เสร็จแล้วได้ adjective ปุ๊บแล้วเราก็ใช้ของเราใช้เป็นที่ผิดเมื่อวานเป็นตรงนี้ text optimize join with join utility ของ test I อันนี้ถูกแล้วนะแต่ว่าถ้ามันเป็น I ตรงนี้มันก็จะมี9ก็คือ decision เนอะจะเป็น363ลบ142ลบ22กับลบ208มันเอาอันนี้บวกกับอันนี้ใช่ไหมบวกกันคิดว่าใช่นะลองดูนะ363.42ลบ142.19ใช่ซึ่งอันนี้ผิดเพราะว่ามัน9มันต้องเอาทั้ง2อันนี้คือ11 362ลบ42ลบ2เอาลองทำเป็นแบบนี้ดูอันนี้ dot val แล้วก็ reshape มันจะได้เข้าดูง่ายๆ2อุ๊บไม่ใช่ผิดต้องเป็น euf นะไม่เป็นไรงั้นเอาอันนี้เราจะต้องเอา11 2อันนี้ต้องหาที่มากกว่าคืออันนี้2อันนี้เอาอันที่มากกว่าคืออันนี้ต้องเอาอันนี้บวกกัน08.25ถึงจะได้คำตอบซึ่งเราทำผิดจะต้องไปแก้ตรง optimize meu ซึ่งแก้ไปแล้วรอบหนึ่งนะอันนี้สมมุติให้ euf เป็นอันนี้นะสมมติเราทำ euf เท่ากับ cal ของ I ก็ได้อันนี้ออกมาถูกไหม euf เนี่ยมันก็ควรจะต้องเป็น max อันนี้เราใช้อันนี้อยู่ max euf max euf max euf เอาตัวเดียวกันเลยแล้วกันนะ euf เท่ากับ euf เป็นอันนี้เสร็จแล้วเราใช้ max อันนี้ซึ่ง max อันลืมอันนี้เราหาทิศทางก่อนว่าเป็นคอลัมน์หรือเป็นโรของตัวที่เป็นตัว decision ดี เสร็จแล้วก็ max ซึ่งอันนี้ผิดถูกไหมเพราะ decision คือ low แต่อันนี้มันดันไปเอาอันนี้กับอันนี้ซึ่งความจริงต้องเป็นอันนี้กับอันนี้ถูกแล้วนี่หว่าเอาไม่ใช่อันนี้กับอันนี้สองอันนี้เพราะงั้นวิธีการของเราก็คือเราต้องเปลี่ยนใหม่เป็น max ตัวเดิมถูกแล้วถ้าเป็น max ตัวเดิมส่วน sum max ก็ต้องเป็นตัวเดิมพอ max ตัวเดิมปุ๊บมันก็จะมี2ตัวคือ index กับตัวค่ามัน index ของมันก็จะมี1กับ2อันนี้คือคอลัมน์ถ้าบอกว่าเป็นอันนี้เป็น row เพราะงั้นอันนี้คือคอลัมน์ก็คอลัมน์ถ้ามีเป็น1 2ก็เป็น1กับ2ถูกแล้ว i ก็เป็น row งั้นถูกแล้วนะข้างล่างถูกแล้วโอเคลองดูนะว่าถูกหรือเปล่าเราลองจาก test case ก่อนเอาเป็นตัวนี้แล้วกันนะถ้าผิดก็ผิดก็แก้ไปตัวนี้จะได้ 7.5 แล้วก็มี10 print of dr ก็เป็น10ถูกไหมน่าจะถูกแล้วนะแล้วตัวนี้อันนี้1100ถูกไหม1100ถูก7.5ถูกไหมถูกใช่ไหมอันนี้เหมือนกัน7.5ถูกหมดอันนี้เป็น EUF EUF ก็ถูกอยู่แล้วเนาะไม่ได้แก้อะไรมันต้องเป็นแบบนี้ถึงจะถูกเนาะเสร็จแล้วพอเราไปใส่ใน optimize เราอันนี้ทิ้งก่อนปุ๊บแล้วก็ optimize join เหมือนเดิมแล้วกันจะเป็น join นะ width ต้อง width join ไปของตัว test i ก็จะได้เท่าเดิมถูกไหมแต่ถ้า optimize ของตัว i ได้เท่านี้นะ optimize ของตัว j optimize ของตัว k เสร็จแล้วก็ให้ optimize ของ enjoy ตัวนี้เป็นค่าอะไรดีเป็น pre แล้วกันเสร็จแล้วถ้าเราเอาตัวอันนี้ i เราให้เป็นอะไร a แล้วกันนะถ้าอันนี้เป็น b j เป็น b ส่วน k เป็น c เสร็จแล้วเราก็เราสร้าง utility to dollar ไว้แล้วของอันใหม่ลบอันเก่าได้เท่านี้155.97แป๊บหนึ่งนะมันสั้นไปก็ถูกแล้วนะเสร็จแล้วก็ b ลบ p แล้วก็ c ลบ p เท่านี้ซึ่งเมื่อกี้ทำก็ผิดอีกรอบหนึ่งก็มันจะไปผิดตัวด้านล่างนี่ถูกแล้ว846.15ถูกปะถูกแล้ว2.82ถูกแล้วอันนี้ยังผิดอยู่เดี๋ยวแก้อันนี้ให้เสร็จแล้วอันนี้ก็น่าเป็น2D เดี๋ยว M ก็จะอันนี้ก็จะแก้อีกทีตอนบ่าย2:40เพราะงั้นเราเรียนกันก่อนเรียนวีคสุดท้ายแล้วเราเรียนจบ5 วีคภายใน5 วันนะฮะ ภายใน5 วันเดี๋ยวปิดเสียง
So we've learned a lot of little bits and pieces of representation that are used to put together a graphical model. And now let's try and take a big step back and figure out how you might put these all together if you actually wanted to build a graphical model for some application that you care about. Now, let me start by saying that this is really not a science. Just like any other design, it's much closer to an art or even a black magic than a scientific endeavor. And so the only thing that one can do here is to provide hints about how one might go about doing this. So let's first identify some important distinctions, and then we'll get concrete about particular examples. There's at least 3 main classes of design choices that one needs to make. The first is whether you have a template-based model versus a very specific model for a concrete fixed set of random variables, whether the model is directed or undirected, and whether it's generative versus discriminative. These are all terms that we've seen before, and we'll talk about them in just a moment. But before we go into the sort of trade-offs between each of these, let me emphasize this last point, which is probably the most critical thing to remember. It's often not the case that you just go in one direction or the other. That is, in many models, you're going to have, for example, template-based pieces as well as some stuff that isn't at the template level. You might have directed as well as undirected components and so on. So these are not a sharp boundary, and it's useful to keep that in mind, that you don't have to go only one direction versus the other in a real problem. So the first important distinction is template-based versus specific. And so what are some examples of specific models? So for example, medical diagnosis is usually a specific model. That is, you have a particular set of symptoms, diseases, and so on that you want to encode in your model. So that's one example. On the other side, on the template-based side, you have things like image segmentation, where you really are going to want to deal with drastically different images within the same model, and that's going to be template-based. There are all sorts of applications that sit in between those two, and you can go either way or incorporate elements of both. So for example, fault diagnosis. Fault diagnosis has, you can think of it as a specific model. That is, you can think about writing a diagnostic model for this particular type of printer. But really, if you're inside a company that's writing a diagnostic tool for your line of 15 different printers, they're going to have shared components. And if you have a component inside printer 1 that also appears inside printer 2, chances are that it's going to have the same fault model. And so you're going to have elements that are unique and elements that are shared. And so once again, it's something that's going to sit at the intersection between the two. That said, once you've decided where on this spectrum you sit, it kind of really changes the way in which you tackle the knowledge engineering problem, because template-based models are usually, not always, but usually have a fairly small number of variable types. So for example, in our image segmentation setting, you have the class label. That is one variable type. Nevertheless, we managed to construct very richly expressive models about this because of interesting interactions between multiple class labels for different pixels in the image. But it's a very small number of variable types, and most of the effort goes into figuring out things like which features are most predictive. So it's really a lot about feature engineering, as opposed to sort of complicated model design. Not always, I mean, certainly not entirely, but the features turn out to play a very big role. On the specific model side, you have usually a large number, because unless you build small models, each variable is going to be unique. So large number of unique variables, each of which requires its own model. And so it's a lot more on the model design, deciding on the dependency and the parameters for each variable separately. A second important distinction is between generative and discriminative. So on the discriminative side, you really should consider that when you have a particular task in mind, a particular prediction task. And when that prediction task is then often better solved by having richly expressive features, richly discriminative features. And then modeling this as a discriminative model allows me to avoid dealing with correlations between them. And so that gives me usually a higher performance model. So you might wonder, well, when would I use a generative model? I mean, if you get such high performance by using richly expressive features. Use a generative model. I mean, if you get such high performance by using richly expressive features. And there's multiple answers to that. One answer is when I don't have a predetermined task, so when the task shifts. So for example, when I have a medical diagnosis task, every patient presents differently. In each patient's case, I have a different subset of things that I happen to know about that patient, the symptoms that they present with, and the tests that I happen to perform. And so I don't want to train a discriminative model that uses a predetermined set of variables as inputs and a predetermined set of diseases as outputs. Rather, I want something that gives me flexibility to measure different variables and predict others. The second reason for using a generative model is, and this is looking way forward in the class, is that it turns out that generative models are easier to train in certain regimes. And specifically, just to sort of make sure, just to sort of say it out loud, in the case where the data is not fully labeled, it turns out the generative models can that sometimes you can't train a discriminative model, but you can train a generative model. So we'll definitely see that when we get to that part of the course. Okay, so having talked about these different regimes, now let's think about what are the key decisions that we have to make in the context of designing a graphical model. So first of all, what variables are we going to include in the model? And regardless of whether we have a fixed or a varying task in hand, we have usually a set of variables that are the target variables. These are the ones that we care about. So even in the medical diagnosis setting, you have a set of disease variables, which are the ones that we care to predict. You might not care to predict all of them in any given setting, but they're usually the targets. We have the set of observed variables. Again, they might not always be observed, but you don't really necessarily care about predicting them. So these might be in the medical setting, things like symptoms and test results. And then the third category might be a little bit surprising. So we might have variables that are latent or hidden. And these are variables that we don't, nor do we necessarily care about predicting. They're just there. Why would we add to our model variables that you neither observe nor care to ever look at? So let's look at an example. Let's consider, imagine that I asked all of you in this class, what time does your watch show? Okay, so each of these WIs is the watch, the time on the watch of each of you in the class. So we have W1 up to WK. Now, these variables are all correlated with each other, but really they're not correlated with each other unless we all had like a watch setting party just before class. Really, what they're all correlated with is Greenwich Mean Time. So you have a model, in this case it's a naive Bayes model, where you have Greenwich Mean Time influencing a bunch of random variables that are conditionally independent given that. Now, Greenwich Mean Time is latent unless we actually end up calling Greenwich to find out what the current time is right now in Greenwich, which I don't think any of us really care about. But why would we want to include Greenwich Mean Time in our model? Because if we don't include Greenwich Mean Time, so if we basically eliminate Greenwich Mean Time from our model, what happens to the dependency structure of our model? We end up with a model that is fully connected. And so sometimes latent variables can simplify our structure. And so they're useful to include even in cases where we don't really care about them, just because not including them gives us much more complicated models. Which brings us to the topic of structure. When we think about Bayesian networks specifically, the concept that comes to mind, the question that comes to mind is, do the arrows, given that they are directed, do they correspond to causality? That is an arrow from X to Y indicative of having a causal connection from X to Y? So the answer to that is yes and no. Right? Very satisfactory. So what does no mean in this case? Well, we've seen, consider a model where we have X pointing to Y. Let me just, do the two variable case. Well, any distribution that I can model on this graphical model, where X is the parent of Y, I can equally well model in a model in the Bayes net where I invert that edge and has a Y pointing to X. So in this example, as well as in many others, I can reverse the edges and have a model that's equally expressive. And in fact, I can do this in general. That is, you give me any ordering that you want on the random variables, and I can build you a graphical model that can represent any distribution that has that ordering on the variables. So you want x1 to come before x2 to come before x3, and you want to represent the distribution P? That's fine, no problem. I can have a graphical model that will do that. But that model might be very nasty. And we've already seen an example of that when we had a case where x1 and x2 were both parents of y, and it was a simple model that looked like this. And if I want to invert the directionality of the edges and put y as a parent of, say, x2, then I have to, if I want to capture the distribution that I started out with, for which this was the graph, then I end up having to have a direct edge between x1 and x2. And so what happens is that causal directionality is often simpler. So to drive this home even further, let's go back to our Greenwich Mean Time example, where we have the Greenwich Mean Time is in some way the cause or the parent of these different watch times that we see in our in different individuals. And let's imagine that I force you to invert the edges. What's it going to look like? Well, So now I'm going to force Greenwich Mean Time to be the child of all of these. And now what? Is this the correct model? No, because this says that all of the watch times are independent, which we know is not the case. And so what we're going to end up with as the model is the same horrific model that I showed before, where everything is connected to everything else. And so causal ordering, although it's not more correct than a non-causal ordering, it's sparser. So generally, sparser as well as more intuitive. So more intuitive, as well as easier to parameterize for a human. So again, you're not forced to use it, and sometimes there's good reasons not to do it, but it's generally a good tip to follow.
So how does one actually construct a graphical model? Do we have in our minds some monolithic P of some set of variables x1 up to xn, and we just need to figure out how to encode that using a graph? Well, maybe implicitly, but certainly not in any explicit form. The way in which one typically constructs a graphical model in practice is by having some variable or sometimes set of variables that we wish to reason about. So for example, we might care about the variable cancer, or maybe even lung cancer. Well, what influences whether we have cancer, whether somebody's going to get lung cancer? Well, if we go and ask a doctor, what is the probability for someone to get lung cancer? The doctor is going to say, well, you know, that depends. And you might say, what does it depend on? And the doctor will say, well, whether they smoke, for example. At which point, you're likely to add the variable smoking as a parent to the lung cancer variable. The doctor might say, well, but that's not the only thing. It might, the probability of cancer also depends, for example, on the kind of work that you do, because some kinds of work involve more dust particles getting into your lungs. And so, again, here's another variable on which you would add as a parent. And then you would go and ask either a doctor or an expert in a different domain, what is the probability that somebody smokes? And if they think about it, they're likely to say, well, that depends. And what does it depend on? Well, maybe their age, gender, maybe the country that they live in, because certainly different countries have different smoking frequencies. And so once again, we're going to extend the conversation backward to include more variables up to the point that we can stop, because if you now ask, for example, what is the probability of gender being male versus female, well, anybody can answer that one. And at that point, one can stop because there's no way to extend the conversation backward. Is that enough? Usually not, because we also need to consider, for example, factors that might help us, might indicate to us whether somebody is going to have somebody has cancer or not. And so we might go and ask the doctor, what are some pieces of evidence that might be indicative here? And the doctor would tell us, for example, coughing, or maybe bloody sputum, and various other things that would be potential indicators. And at that point, one would say, well, okay, what is the probability of coughing given lung cancer? And again, one would now extend the conversation backward to say, well, other things might cause coughing, for example, having allergies. And so once again, we would go from here and extend backward to construct a graphical model that captured all of the relevant factors for answering the queries that we hear about. So that's the structure of a graphical model. Now let's talk a little bit about parameters, the values of these parameters, and what makes a difference here. So here are certain things that really do make a difference to parameters. Zeros make a big difference. And when we talked about diagnosis, we saw that many of the mistakes that were made in early medical expert systems were derived from the fact that people gave zeros to things that were unlikely but not actually impossible. And so zeros are something to be very, very careful about, because you should only give probability 0 to something that is impossible, perhaps because it's definitional. Otherwise, things really shouldn't have probability 0. Other things that make a difference are sort of weaker versions. So, for example, order of magnitude differences, the difference between a probability of 1 over 10 versus 1 over 100, that makes a difference. It makes a much bigger, whereas small differences like 0.54 versus 0.57 are unlikely to make a difference to most queries. Finally, it turns out the relative values between conditional probabilities make a much bigger difference to the answer than the absolute probabilities. That is, the comparing different entries in the same CPD relative to each other is a very useful way of evaluating the graphical model and seeing whether the values that you use for those relative ratios really make sense. Finally, conditional probability tables are actually quite rare except in small applications. In most cases, one would use structured CPDs of the forms that we've discussed, as well as a variety of other forms. So let's talk a little bit about structured CPDs, because those are actually quite important. And we can break up the types of CPDs that we've talked about along two axes. One is whether they're intended to deal primarily with discrete or with continuous variables. And on the other side is whether the type of structure that they encode is context specific, where a variable might make a difference in some circumstances and not in others, versus aggregating of multiple weak influences. And so let's give an example of each of these categories. So for discrete and context specific, we had tree CPDs as an example. For discrete and aggregating, we had sigmoid CPDs, as well as noisy or noisy max, or any one of those, that family. For continuous CPDs, we didn't actually talk about context-specific representations, but one can take the continuous version of a tree CPD called a regression tree, where one breaks up the context based on some thresholds on the continuous variables. And that is a context-specific version of a continuous CPD. And finally, the aggregating version of a continuous CPD, the Gaussian or conditional linear Gaussian is an example of that. By the way, note that the conditional linear Gaussian that we talked about is context-specific on the discrete variables. Finally, it's important to realize that a model is rarely done the first time you write it. And just like any code design, model design is an iterative process where one starts out somewhere, tests it, and then improves it over time. So importantly, once one constructs a model, the first thing to do is to test the model, ask it queries, and see whether the answers that come out are reasonable. There is also a suite of tools that do what's called sensitivity analysis, which means that one can can look at a given query and ask which parameters have the biggest difference on the value of the query. And that means those are probably the ones that we should fine-tune in order to get the best results to the query. So we're once with dependencies to the model that can capture the kind of structure that's in it. So we've learned a lot which depends extender to get the best results on the value of tools that do what's called sensitivity analysis.
For some application that you care. So sort of in each patient, so on the discriminative side, you really should consider that when you have a particular task in mind, a particular prediction task. And when that prediction task is then often better solved by having richly expressive features, or richly discriminative features, and then modeling this as a discriminative model allows me to avoid dealing with correlations between them. And so that gives me usually a higher performance model. So you might wonder, well, when would I use a generative model? I mean, if you get such high performance by using richly expressive features, and there's multiple answers to that. One answer is when I don't have a predetermined task, so when the task shifts. So for example, when I have a medical diagnosis task, every patient presents differently. In each patient's case, I have a different subset of things that I happen to know about that patient, the symptoms that they present with, and the tests that I happen to perform. And so I don't want to train a discriminative model that uses a predetermined set of variables as inputs and a predetermined set of diseases as outputs. Rather, I want something that gives me flexibility to measure different variables and predict others. The second reason for using a generative model is, and this is looking way forward in the class, is that it turns out that generative models are easier to train in certain regimes. And specifically, just to sort of make sure, just to sort of say it out loud, in the case where the data is not fully labeled, it turns out the generative models can sometimes you can't train a discriminative model, but you can train a generative model. So we'll definitely see that when we get to that part of the course.